Oh, geez. My microphone was muted the entire time. Thank you for doing that. Oh, geez. So sorry. Okay, yeah, I spent a good 5 minutes talking about nothing to you guys, apparently. Sorry. Jeez. What? Okay, sorry about that. My goodness. Awkward. Yes. Yes, it is. It's only awkward if you make it awkward. I'm not making it awkward right now. That's for sure. So you guys heard nothing that I said over the past 5 minutes. So dang, I'm so sorry. All right. So what I said basically was today is the last lecture that's live. Starting on Monday, you'll just come in and you will have watched the next video already. And you'll ask questions about that video, and then maybe homework problems or whatever. We'll just go over, general questions that you might have, or even specific questions about problems and material and stuff like that. So sorry about that. So today we're gonna get into probability and counting techniques, and then next time you'll watch a video on independence and conditional probability and Bayes' theorem. And then after that, there's like a little bit of a review problem section. So just hang in there. It's going to be pretty good. But yeah, today is going to be probability and counting techniques. So let's get right to it. I don't want to go through the whole 5 minutes that I just did, but that's basically what I said was today's the last live lecture. Monday, there will be a Moodle meeting or a Zoom meeting on Moodle that you can join. And I know a lot of you said that you have internships, so you might not be able to make it all the time, which is fine. Just watch them at your leisure. Watch the lectures. Try not to get behind. If you want to get ahead, you're more than okay to do that. All the lectures are already on YouTube in the YouTube playlist, Statistical Methods Lectures playlist. So feel free to get ahead or rewatch or whatever you want to do. So here we go. 2.2 Axioms and Interpretation of Probabilities. Probability is the likelihood that an event will occur out of a certain number of occurrences of an experiment. So I like to think of it as like, okay, if I do this experiment 1,000,000 times, how many times will this event occur? And the infinite limit of that. So basically, like, if I do the experiment infinitely many times, then half the time I'll get heads and half the time I get tails if I'm flipping a coin, assuming it doesn't land on its side. So that's how I think of interpretation for probability. That's my personal opinion of what the best interpretation is of probability. Is the infinite limit of the experiment and the infinite limit of the probabilities or percentage of the time that this event will occur. So that's how I like to think of probability. The axioms of probability are that probability cannot be negative. It has to be greater than or equal to 0. Furthermore, probability is always less than or equal to 1. So basically the probability of the sample space is 1. Something in the sample space will occur. Otherwise, you've not put everything in the sample space. So that is the first thing. Probability is non-negative and probability of the sample space is 1. So probability is always between 0 and 1, basically. So probability is always between 0 and 1. Guaranteed. Now the third axiom of probability, it kind of makes sense, but you have to kind of really dig in to see what's going on there. And the third axiom says if A1, A2, etc. are an infinite collection of pairwise disjoint events, then the probability of the union is just the sum of the probabilities. So basically, AI intersect AJ equals the empty set if I is not equal to J. So they're pairwise disjoint. That means any two that you compare, they will not have an intersection. Then, this is an axiom, the probability of the infinite union is the infinite sum of individual probabilities of the events. So those are our three axioms of probability. They're our starting place, they're what everything else is built off of, and We have to always satisfy these three if we're talking about probability. So any questions before we really get kicked off here? Again, sorry about that. My goodness, I'm so sorry. Rookie mistake. Except I've been doing this for a long time, so it should not have happened. Okay. Let's go on to a proposition here. It says that the probability of the empty set is equal to 0. So this is the result. How can we prove it? Well, how could we prove that the probability of the empty set is 0? Well, if we set every set equal to the empty set, and we take the infinite union of empty sets, well, we just get the empty set because there's nothing in any of the sets. Good question. So Ben says, what if AI and AJ are equal? So back here, that's fine. Then there are this, oh, sorry. Okay, so AI and AJ are equal only if I is equal to J. So the assumption here, Ben, is that in number 3, A1 is not equal to any of the other sets, A2, A3, etc. So AI is equal to AJ only if I is equal to J. So that's basically this an alternative way to say this assumption. So AI equals AJ only if I is equal to J. Good question. So it's just like an alternative phrasing of the condition. Well, not quite, but it's another part of it. Because if they were equal, their intersection, AI intersect AJ, would be equal AI. So yeah, good question. All right, so back to our proof that probability of the empty set is 0. On the left, if we sum up, or if we union all the empty sets, well, we just get the empty set, because the union of empty sets equals the empty set. All right, if all the empty sets are being unioned, well, there's nothing in any of them, so the union is just the empty set still. So that's how we go from here to here. Union of empty sets is still empty. But they're all pairwise disjoint because they have no intersection, right? So empty set intersect empty set is empty set, therefore pairwise disjoint. So all the empty sets are pairwise disjoint. So this one is equal to this one by axiom 3. So the probability of the empty set is equal to the infinite sum of probabilities of the empty set. The only way that's true is if the probability of the empty set is 0. You can't add a number to itself infinitely many times and equal the original number, only unless the probability of the empty set is 0. So basically A equals the sum of A. I goes from 1 to infinity only if A is 0. So that's how we can imply that the probability of the empty set is 0. Again, I'm not going to worry about proofs or anything on the exam. I just want to be thorough here on the presentation. So another proposition is that a finite sum can be broken up as, or the probability of the pairwise disjoint AI. Finite union is the finite sum. So finite union versus finite sum. So we should say pairwise disjoint here. So if AI is a set of pairwise disjoint sets, then the finite union, probability of the finite union is the sum, the finite sum of the individual probabilities. All you got to do is set the rest from k all the way up to infinity equal to the empty set. And then you can turn it into an infinite union, use axiom 3. And then break up the summation. Break up the summation from 1 to k, and then k plus 1 to infinity. And then from 1 to k, you have the original. from k plus 1 to infinity, you have the empty set. And so we know all of these are 0. So this summation is going to be 0. So we have just this sum right here. These unions are equal because you're only unioning with empty sets after k. So k plus 1 to infinity, it's all empty sets. So you're not gaining anything new. So that means the union I equals 1 to k ai equals union I equals 1 to infinity ai, since ai equals empty set for I greater or equal to k plus 1. So those two unions are the same. So again, I don't want to spend a whole lot of time on proofs and things like that, but just to give you an idea of what one direction you could go with probability is very theoretical. We're going to focus on mostly computational parts of probability and statistics. So a graduate level course in probability and statistics would go into all the theory, but for us, we're going to be mostly computational. So just understanding what it is, how to use it, and doing examples and making sure we understand what people are telling us when they give us all these things. That's the kind of the goal of the course, in my opinion, is really just to be able to understand and function in the world where numbers are constantly being thrown around. So you really want to understand what's going on. If you're a math major, then maybe you want to dig into the theory. You definitely want to dig into the theory. But all right, let's go to this example here. It says example, we got a coin toss. The sample space we know right here is the sample space set of all outcomes. And the probability of the sample space is probability of heads union tails, because sample space is equal to heads union tails. So S equals HUT, or H union T. And what do we know? We know the probability of the sample space is 1. Well, these are disjoint. Heads and tails are disjoint. So H and T are disjoint. So this one can be broken up into these two. Probability of heads plus probability of tails equals 1. And so then we could subtract probability of tails from both sides and get that the probability of heads is 1 minus probability of tails. Of course, we know this already, like 0.5 is 1 minus 0.5. So not a big deal, but the important thing to note is this proposition. It's what we call the complementation rule. So complementation rule. And the complementation rule says probability of the complement is 1 minus the probability of the original event. So you say, okay, what's the probability of getting tails? Well, it's 1 minus probability of getting heads. And the proof is very similar. We're not going to go through the proof. It's very similar to the computation we did in the example. But it's called the complementation rule. It is so, so important. Let me put like 2 stars here. So important, this complementation rule. So important. All right, let's look at this example. It says accidents in a factory either occur during the day or occur during the night, and either they're a result of human error or equipment malfunction. So the sample space is day human, night human, day equipment, or night equipment. And we have the individual probabilities here, which are just the percentage of the errors. How do you know H union T is 1, not 0? I only know that H union T is 1 because probability of the sample space is equal to 1. So probability of the sample space is equal to 1. Probability of S equals 1, and H union T equals S. So probability of H union t equals 1? Good question. It's more like implies. So this arrow here is like implies. So that's how you should read that arrow. So S equals A union A complement implies probability of S equals probability of A union A complement. Yeah, therefore, or implies. Either way. Did I kind of answer both your questions? Okay, sweet. All right, let's look at this example. Probability of accident during the day. Well, probability of day is going to be probability of day human union day equipment. And those are disjoint because human and equipment malfunctions are disjoint. So it's going to be probability of day human plus probability of day equipment, which is going to be 0.1 plus 0.35, which is 0.45. And then probability of night is going to be 1 minus probability of day, since night union day equals the sample space. Or it's either night or day. So those are like the only two options. You could break it down further into night, human, day equipment, etc. But if you just look at night and day, those are your only two options. So the night union day is equal to the sample space. So they're complements. So probability of night is 1 minus probability of day. So that's going to be 1 minus 0.45, which is 0.55. And you could add those up, like 0.13 plus 0.42, which are night human and night equipment. You get 0.55, so same thing. But we just use the complement rule to get there because it's a little bit, actually it's a lot easier in a lot of examples that we're going to see later. Keeping this complement rule in the back of our minds is really, really good. Really, really useful. Okay. Interpreting probabilities. Assume an experiment that is performed n times. This is basically what I mentioned when we were introducing probability. Let's say we have an event A. N is the number of times A has occurred. And we take the percentage or the ratio of the number of times of A occurs out of the number of times the experiment happens. And we call that the relative frequency of occurrences of A. For small n, the value will fluctuate as n gets large, going to infinity. In the long run, this will converge to a single value probability of A. And that's the interpretation I think is best when thinking about probability. I don't like to think of probability as like, okay, I'm about to roll 2 dice. On the next roll, I have a 1 out of 6 chance of getting doubles. I don't like that. I say, okay, out of 1,000 tries, then, 16% of the time, or 166, times, I'm probably going to get doubles. That's the way I like to think about probability. So I like to think of it as, okay, if you do it in the long run, what happens? So it's kind of like a casino. The casino doesn't care what happens on a single time. Like a slot machine, sure, a slot machine could pay out somebody big money one time, and the person's like, wow, that happened, and I had such a low probability of that happening. Really, what the casino is worried about is what happens in the long run. If people are, like, on average losing money, that means the casino is on average gaining money. So they don't care what happens each time. They care what happens in the long run, because that's what probability is all about. In the long run, large numbers of experiments, not just one experiment, not just the next experiment, but the next 1 million experiments. The next 1 million times a slot machine is pulled, what's going to happen? So that's kind of the best interpretation. Sorry, I went to the casino example. It's just a good example for, the reason they make money. It's because people don't really understand probability. They think, oh, I'm gonna beat the odds. I'm gonna beat the system because I'm going to whatever. And with slot machines and even like games like roulette, you're already guaranteed to have like a losing chance. So that's why the casinos make money. Anyway, just throwing that out there. This is the best interpretation, in my opinion, of probability. Now, probability of a union. This is also extremely important. So this is another extremely important property of probability. It's probability of A union B. So probability of A union B is equal to probability of A plus probability of B minus probability of the intersection. So think about it. Probability of A union B would say, okay, if I take probability of A, that's everything here. If I take probability of B, that's going to be everything here. Oh no, we counted the intersection twice. So we counted the intersection twice, so we have to subtract it once. So we're counting intersection twice. So subtract once. You nailed it, Reed. House always wins. Now that doesn't mean they always win. It means in the long term, they will win. It's probabilistically stacked against the player. At least a lot of like games, slot machines, stuff like that. There are some skilled games, whatever, where you play against other players and not the house, but the house gets a cut. But most things in a casino are stacked against you. Just like a carnival and, these arcades. A lot of those games are like intentionally programmed to be hard to win. So it's more like in a probabilistic sense, you're going to lose. All right. So that's probability of a union. You can go on to probability of a union of 3 sets. Gets a little more complicated. You add the individual sets, probabilities, subtract the intersections, the pairwise intersections, and then add the single intersection. So think about that one more time. A counts everything here. B counts everything here. And C counts everything here. Oh no, I counted those intersections too many times. So if I subtract A intersect B, well, where's A intersect B? It's right here. So I subtract it once. I subtract A intersect C, which is here. And I subtract B intersect C, which is here. So I've actually subtracted that very middle 3 times, so it's not there anymore. So I have to add that middle back in. So I have to re-add the middle right here. So it gets added back in. And 4, you could try. Yeah, that's nasty. So we're not going to go into 4. You could do it, but I'm not going to worry about it. Just say if you have to do it, good luck. This is what we call a distributive property of intersection over union. So probability, so let me just write down set theory property A union B intersects C is equal to A intersects C union B intersects C. So intersection distributes over union. Intersection distributes over union. And furthermore, A intersect B union C is equal to A union C intersect B union C. So these are two properties I just want to point out. And then from those two properties, these intersections are easier to see. So yeah, Logan, the pairwise intersections were subtracted, which means that middle overall intersection was subtracted 3 times. Well, it was added 3 times and then subtracted 3 times, so now it's not there. So we have to add it back in 1 time. All right, so let me color in A union B. A union B would be everything here in red that I'm going to shade. So that's A union B. And now think about where A union B intersects C. Well, we can see that that's clearly the green shaded portion. So that's A union B intersected with C. Well, let's think about this. A intersects C. Let me just redraw the diagram. And A intersects C will be right here. B intersects C will be right here. And then I need to subtract away 1 time this portion in the middle. So you could do that. Or you could say, okay, well, A union B intersects C by property 1 is A intersects C union B intersects C. And then I can use the property of the unions to derive it. So that was basically like the previous property. All right, determining probabilities systematically. Sample space S with simple events E1, E2, E3. Well, if they're simple, they only have 1 outcome. And let's assume they're all disjoint, pairwise disjoint. So then the sum of the probabilities would be 1, because all of the events union up to be the sample space. So S is equal to the infinite union of EI. So their sum adds up to 1. And event A is represented as a subset of those simple events. So it's a subset of simple events. So any event is a subset of simple events. So that's all this is saying right here. Well, now we can determine probability if they are all equally likely, kind of like the faces of a die or sides of a coin, etc. So let's say we have a finite number of equally likely outcomes. Then the probability of the sample space we know is 1. So probability of S equals 1. Well, probability of S then is the union of the individual events, which we can add this way right here. So we can just add, and each of the probabilities is equal to P. And P is a constant, so I can pull it outside the summation. So summation I equals 1 to N, P equals P times the summation I equals 1 to N of 1. And summation I equals 1 to N of 1 is just N. So P times 1 plus 1 plus 1. N times is P times capital N. Which is how we get that right there. And so N times P is equal to 1, so P is equal to 1 over N. And so basically the number of events in your sample space tells you the probability if the probabilities are all equally likely. So this assumption is that the events, the simple events, are all equally likely. Just like, the faces of a die or flipping a coin or something like that. The two sides are equally likely. If you have a 6-sided die, 24-sided die, whatever sided die you have, the assumption would be that all the faces are equally likely. Now, if you think about that, in the real world, our dice or is a die the same on every side? Well, no. On the 6-sided face, or on the 6 face, there are 6 little spots cut out, and on the 1, there's only 1. So there's actually more mass on the 1 than there is on the 6. Well, people thought about that and they were like, well, we have to find a way to make it work out. So they actually make the 6-sided die have a little bit non-uniform materials, or they cut out less of the whole to make it the same amount of mass on every side, so it's no longer unfair. So that way 6 is not more likely to pop up because 1 is heavier. Now 1 and 6 have the same amount of mass on both sides and they're now equally likely. So casinos take that into account. So the dice in a casino should be fair and will be fair, but the probabilities of the machines and games and roulette and the way things are set up as far as the rules go are not fair. Well, actually they're not fair. They're fair if you are okay playing with it. So it's just not likely that you're going to win. It's more likely that you're going to lose. We'll talk about roulette at some point. Maybe. All right. So basically the takeaway is that the probability of an event that is equally likely, you just take the number of outcomes in the event divided by the total number of outcomes in the sample space to get the probability of your event if all the outcomes in the sample space are equally likely, or if all the simple events are equally likely. And you can visualize it with the Venn diagram. Not going to do that. Don't worry about that. Counting techniques, we do want to start here. We have like 35 minutes left. I should be able to get to where I want to get. I think I want to get all the way through 2.3 before Monday. So cool. Let's get into counting techniques. You may or may not have seen these before. If you're computer science, you've probably seen these before. If you took advanced math in high school, you might have seen these, but just depends. So the counting techniques are really ways for us to count the number of outcomes in our sample space or in our event and things like that. So at least that's the way we're going to use these counting techniques. They're extremely useful. So the product rule for ordered pairs basically says if I have a certain number of options for A and a certain number of options for B, then the number of possibilities for combining A and B into an ordered pair is n1 times n2. So basically right here. Think of this as like, so example, if I have 10 shirts and 4 pairs of shorts, how many outfits can I make? I do this in 311 when I go over it. Yeah, I may not teach you how to win big, but I'll teach you how not to lose big. And if you go to a casino, you're going to lose. Just saying. It's in the long term. If enough of you go, enough of you will lose. You may be the one person that wins, but that's the thing. That's the hitch. Everybody gets into that psychology of, oh, I'm going to be the one person. And everybody gets in there like, man, I actually won something. And that's the thing. Like, it's a psychology game. If you don't really sit down, look at the numbers, you're like, I think I can do it. I think I can be that one person that's going to win. And that's how they draw you in. They're like, oh, see, this person won $100,000, you know? And like, that's the one person out of 100,000 people that actually won $100,000, you know? So counting techniques may or may not include counting cards. We'll see. I'm probably banned from actually going over counting cards, so I'll leave that to your self-study. But yeah, stick to poker and blackjack. More skilled games. At least you have people to play with, not just playing against some computer program that's already like guaranteed to make you lose. Okay, let's see. So how many outfits would be possible here? Well, for each of the 10 shirts, I can pair it up with any of the 4 pairs of shorts. So for shirt 1, I have 4 possibilities. Shirt 2, I have 4, and then 4. 10 times, so that's 40. 40 outfits. Which is really just 10 times 4, which is what the product rule is saying. For each of the first objects, you have however many of the second object that you can pair it with. And that's the product rule. And then you can generalize that to however many objects you want, not just 2, but maybe you could throw in a hat and shoes and, whatever, belts. And they could create so many outfits, So it can generalize to any number of objects, not just 2. You could draw a tree diagram, but I never do, so I'm going to skip it. How about that? Permutation and combination. Let's see, I think I want to go over these a little more like in depth than what we have here. So permutation is a number of ordered ways to arrange objects. So permutation is an ordered arrangement of objects. And let's say I've got 4 people and 4 chairs. So I've got 4 people. I've got Ben, I've got Robbie, Hannah, and Reed. And I want to know how many ways they can be seated in 4 chairs. So we'll say chair 1, chair 2, 3, and 4. Okay, so how many ways can I seat the 4 people, Ben, Robbie, Hannah, and Reed, in the 4 chairs, chair 1, chair 2, chair 3, chair 4? So I look at the first chair and I say, okay, how many options, how many people can I stick in the first chair? Well, then I've got 4 options for that first chair. And for each of those options, I have 3 options that I can put in the second chair. So any of the 3 remaining people that I don't put in the first chair can go in the second chair, and then 2, and then 1. So it's actually 4 times 3 times 2 times 1. So 4 times 3 times 2 times 1. Then you might say, okay, well, what if I had 5 people? It's a question. Or what if we have 6 people? So what if Johnny and Susie also are here? Well, then I do the same thing. I look at the chairs. I could say chair 1, 2, 3, 4. And now I say, okay, for chair 1, how many people can I put there? Well, I can put, 6 people there. And then any of the remaining 5 can go in chair 2. Any of the remaining 4 can go in chair 3. And any of the remaining 3 can go in chair 4. So 6 times 5 times 4 times 3. So this is actually 6 factorial over 2 factorial, which is 6 factorial over 6 minus 4 factorial. And this up here is really just 4 factorial, which is 4 factorial over 0 factorial, which is 4 factorial over 4 minus 4 factorial. So this is the general form. Given n objects that we want to permute among k objects, where k is less than or equal to n, then the number of ways to do so is npk, which is n factorial over n minus k factorial. This is what we call the formula for permutation of objects. Okay, well, that's cool. What if we don't care about the order of the chairs now? So what if the order of the chairs doesn't matter? What if the order of the chairs is unimportant? So then the answer is, how many ways can we arrange the chairs or rearrange the chairs without changing the people. Well, for each spot, I could put any of the 4 chairs in that spot. So let's say I've picked the people: Ben, Johnny, Hannah, and Reed were chosen. How many ways can I change the chairs now? Well, Ben, Johnny, Hannah, and Reed can get any of the 4 chairs. So let's say Ben has 4 options for his chair. Johnny has 3 options, Hannah has 2 options, and Reed has 1 option. So there are 4 factorial ways. There are 4 factorial ways to rearrange chairs without changing people. So this means we've overcounted. This means if we don't care about chair order, so this means if we don't care about chair order, then for each possible set of people, we've overcounted by 4 factorial. So what do? Divide NPK, or what should I say? 6P4 by 4 factorial. So then, if we don't care about the order of the chairs, we would have 6P4 over 4 factorial, which would be 6 factorial over 2 factorial over 4 factorial, which would be 6 factorial over 4 factorial, 2 factorial. So basically you divide by the number of ways to yeah, kill the order. Why must we use multiplication instead of addition? So because let's see, any of the 4 people, Ben, Johnny, Hannah, Reed, let's say Ben, he has 4 options for any of the chairs. And then for each one of those, Johnny then has 3 options for any of his remaining chairs, and Hannah has 2 options and Reed has 1 option, or whatever. So the idea we had with the multiplication rule or the product rule was that for each option, the other objects, or in this case the other people, have a different number of options or objects or options for their chair. So then the way that we were introducing the idea was with t-shirts and shorts. We said, okay, for the first shirt, we could be any of the 4 pairs of shorts. So that was 4 plus 4 plus 4 plus 4, 10 times, which is 10 times 4. That's the same thing that's going on here, except we have a lot more additions going on. So we just condense it all down into multiplications. I'm not sure if that kind of answers your question of why we use multiplication instead of addition. We are, I guess, under the hood using addition, but it's really just a condensed addition into multiplication. All right, because Ben could be any of the 4 chairs, and for each of those 4 possibilities, there are 3 options for Johnny's chair, etc. So it's like 4 times 3 times 2 times 1. And this is what we call a combination or an unordered arrangement. So we call this nck, and that's n factorial over k factorial n minus k factorial. And this is what we call a combination. And it's an unordered arrangement. Oh man, unordered arrangement. Whereas permutation we had up here was ordered arrangement. So that is the discussion I really want to have about combination and permutation. You can look at that example that tries to introduce it, but I like this approach better. So permutations, right here, same formula. Combinations right here. Permutations are ordered, combinations are unordered. So if we have the same people, we don't care which chairs they sit in, possibly. That would be a combination. How many ways can we combine the people or just select a subset? Okay, let's see. Example, let's say my iPod. Man, this is old. 100 songs on my iPod. 10 of them are Beatles songs. I have my iPod on shuffle. What is the probability that the fifth song played is the first Beatles song? Or not the first Beatles song, but the first song that's played that's actually a Beatles song. Not that I have an ordering of my Beatles songs, but that the first Beatles song that I hear is the fifth song played. So let me just kind of reword that. The first song played that is by the Beatles is the fifth song played. So that's the more precise interpretation of the question, or statement of the question, I should say. So the first song played that is by the Beatles is the fifth song played overall in the playlist. So we want to find what's the probability that this happens. So how often does this happen, that you play 4 non-Beatles songs and then a Beatles song? How often is that going to happen when you randomly shuffle your playlist? And we assume that once a song's played, it's not going to pop up again in the playlist. All right, so number of ways to select the first 5 songs is 5 times 100 times 99 times 98 times 97 times 96, because I have 5 songs. The first song could be any of the 100 songs. The second one could be any of the remaining 99, etc. So that's just 100 permute 5. Then the number of ways to select the first 4 songs if they're not Beatles songs is 90 permute 4, because I've taken out 10 because 10 of the songs are Beatles songs and I don't want those to show up on my first 4 slots. And then the number of ways to select the 5th song, which is going to be a Beatles song, is 10 because there are 10 Beatles songs on my iPod. So then in the numerator, the number of outcomes in my specific playlist is 10 times 90 permute 4. And then the total number of outcomes in my playlist would be 100 permute 5. So it only happens like 6.78% of the time. So 6.78% of the time the playlist will be like this. And by that we mean non-Beatles, 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 and then Beatles. So I want to take a second, make sure this is clear. I know it's a little confusing at first, but we can talk it through and make sure everybody's on board. I think I want to change something really fast. Okay. Any questions? So you could think of this as like a counting principle as well. Like it's a multiplication principle happening inside of, you know, this problem. So like this is like the number of ways to choose the first 4 songs. And this is the number of ways to choose the 5th song. And we multiply those two numbers of ways to get the number of ways to choose the first 5 songs the way we want them to be chosen. Non-Beatles, 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 and then Beatles. The bottom is just the first 5 songs regardless of which song. It doesn't matter which song could be played. The first 5 could be all Beatles, or the first 5 could be non-Beatles, or any mixture of the two. So that's the bottom. The denominator is any number of ways to select the first 5 songs. Whereas the numerator is the specific way we want to select the first 5 songs. Okay, cool. Let's look at this example here. Oh, yeah, we're almost there. Let's finish this example. We'll be done. This is where I wanted to be for today. And the next video picks up right there in 2.4. So this example says 15 Apple and 10 Dell computers are bought. 6 of them will be given to students. What is the probability that exactly 3 will be Apple? So we'll call it the event A3 equals exactly 3 of the 6 are Apple computers when we give them away. Well, the total number of ways to give away 6 computers would be 25 choose 6. This notation I didn't really go over is n choose k is the same as n ck is just n factorial over k factorial n minus k factorial. So it's the same notation, it's just it's a different notation, but it means the same thing. It means unordered grouping, unordered pairing or grouping of the elements. So you want to pick 6 computers at random from the 25 computers you have all together. Well, that's right here. 25 choose 6, and you get this number 17,771,00. So that's 177,100. Number of outcomes where we have exactly 3 are Apple is, well, I choose 3 to be Apple, and then that means I have to choose 3 to be Dell. And 15 choose 3 times 10 choose 3 is 54,600. So this means the probability of choosing exactly 3 Apple would be 30.83. So 30% of the time, if we randomly choose 6 computers, 3 of them will be Apple and 3 of them will be Dell, 30% of the time. So 30% of the time, we will randomly choose 3 Apple computers. Well, what's more likely is that we're probably going to pick more than 3 Apple computers since there are 15 Apple computers. But, you know, we're not going to get into that right now. Second part of this example, well, let's hang out here for a second, see if there are any questions, and then we'll wrap it up with the second part of this example. And just make a note here. This is 3 Apple. Number of ways to choose 3 Apple. And this is the number of ways to choose 3 Dell. So just so that's clear. Okay, let's move on to part B. Part B says, what is the probability that at least 3 will be Apple? So we have A3 already, but what's A4, A5, A6? So probability of A4 will be 15 choose 4, and then 10 choose 2 over 25 choose 6. Because now I'm picking 4 Apple computers and 2 Dell computers. Probability of A5 is similar, 15 choose 5, 10 choose 1, 25 choose 6, and then probability of A6 is 15 choose 6 times 10 choose 0 over 25 choose 6. And now all I do is add those individually. So probability of A3 plus probability of A4 plus probability of A5 plus probability of A6, which is, and it turns out to be something like 54,600 plus, so that was the numerator of A3. These all have the same denominator, which is 177,100. Let's see, the 15 choose 4 times 10 choose 2 turns out to be 60. I think it's 61,425. Then 15 choose 5, 10 choose 1 is 30,030. And then 15 choose 6 is 5,005. And that comes out to be 0.8530. So 85% of the time, we'll have at least 3 Dell computers in our random selection of 6, or sorry, at least 3 Apple computers in our random selection of computers. And there's a little note here at the end of the slide, and that says, oftentimes it's much easier to work with probabilities if we define them in the context of a variable. We're going to do this in chapter 3, but it's just kind of giving you like a little tease, a little preview of the next chapter, so heads up. Basically here, x would be the number of Apple computers we selected, and then we'd be finding the probability x equals 3 or probability of x greater or equal to 3, depending on which part you're looking at in this example. Part A was probability x equals 3. Part B was probability x is greater or equal to 3. So sweet. We're basically done for today. We'll pick up right here next time with the next video. So you go ahead and watch that over the weekend, I guess, before Monday morning at 9:45, and then we'll come in. You guys have questions or whatever, I'll answer those. You guys have a good weekend. Right after you smash the like button, I'll talk to you later. See ya.